sir. Good evening, everybody. I welcome you all on behalf of Scope TNM to this session on traveling wave fault location system. So, this is me, Jayant Dev. I am a product specialist here, and I am supported by Mr. Nilere, who is a lead product specialist here at Scope TNM. Okay, let's go forward. Now, this will be agenda for today's session. First, we'll look at the introduction of the traveling wave fault location system, why we require that, and what they are to be exact. What is the principle of fault location in a transmission? We'll look at the system description, what they should be, how a traveling wave fault locator system should look like. Then we'll see some field applications, and then we can have a Q&A session. Okay. Now, just as you guys are very learned, but still, I took an opportunity to just brush up some basic concepts before coming straight to the point. So this is our power system, which comprises of generation plants, as well as our step-up transformer. Then comes our primary transmission, primary distribution, then secondary distribution. And we have our consumers, all sort of loads, be it industrial, be it domestic. Now, a fault can arise anywhere in a system, as we know, but whenever there is fault at the node ends, node means like if it is at generation end or if it has load end, it can be taken care of without hampering any further system, right? Bypassing is far more easier if it happens at these nodes. But what if the fault happens in the transmission line? Well, transmission lines are more or less the lifeline of a power systems. Just like we have arteries in our body to carry blood throughout the body, and the oxygen and all other necessary components to carry out our basic metabolism activities in the body. So this is how important transmission line is for us. Now, as we saw, transmission lines that are mostly out in the open most of the times are most prone to any kind of atmospheric calamities and all sort of things that there are when they are situated out there, because the kind of terrain they are put in is quite classified. They can be hilly areas, they can be sandy areas, they can be full of humid conditions and whatnot. So if there is a fault, and I'm talking about transmission line faults here. So if there is a fault, pinpointing that fault, because without going there physically and at those fault, we cannot, make that particular line open or that line on. And until we do that, there will be a complete interruption for particular dedicated line. So going to attend that particular fault in that particular transmission line is quite an important task, and it's quite a tedious or an overwhelming task at the same time because of the geographical area that they cover. Transmission lines, they run to the span of hundreds and thousands of kilometers in a single go. So finding out faults in them is quite a tedious task. And if we go with the conventional methods, like visual inspection, when we talk about visual inspection, we are very well aware about this thing of patrolling. We send out our teams in 2s and 3s to see where exactly the fault happened. So, patrolling method, first of all, given the terrain, suppose if you guys are from Mumbai, let's say we have actually a situation in Navi Mumbai where you have got transmission line, extensive transmission line of 400 kVs between Vashi and I can't remember the name. So there exactly, those transmission lines, they actually are going through the backwaters of the sea. So their patrolling is quite tough. Same as the condition if you have got hilly areas. So there the patrolling gets quite tough for the people, as it consumes a lot of time. Then you have to rely on people's diagnostics ability. They have to be quite keen on finding the faults. That is also a problem. Then comes your commercial implications, because the more time it takes, the more is your downtime, at the end will all culminate into your commercial aspect or your commercial load. So visual inspection and good when you are dealing with say 30 kV or 11 kV line, that is fine because they don't run to such extensive distance, and mostly if you have got one line down, you can go ahead with something else. In case of transmission lines, let's say 220 kV or 400 kV and above, they are quite critical. If they are down, the associated loads are down, and you can have quite some problem. Transmission of your power. Now the same is the case with comes the problem with the transient faults. So suppose there is a tree touching your transmission tower, it will touch and it will go away. So your breaker will open for a moment and then it will auto reclose. With the help of the auto reclosure function, it will close back, and you will never get to know where exactly is this thing happening. Where is this impediment coming into picture? Where exactly is this tree touching your transmission line and then going away? So that is again not covered when you are dealing with your patrolling or visual inspection. So what exactly to do? To take care of it, we have more or less a conventional method that has been with us for quite some time now. We call it impedance method. As you guys are from transmission system, so you guys must be very well aware of this particular phenomena. Here we calculate voltage and current from the associated phases of a line, right? So we have got input from our PTs and we have got inputs from our CTs, and we calculate V by I. Whenever the impedance in that particular zone of ours is less than the target area, or less than the target value, or less than the triggering value, that particular system, it gets triggered. That is our fundamental concept, because it signifies whenever there is fault, your current will go up and your voltage will drop down. That is our fundamental concept. So this is how your impedance method works. As you can see in this diagram, it is a very typical diagram, and you all guys can associate with it. So this is one solution that is available, but is it a complete solution? Is it a solution that fulfill all our needs? Look into it. Now, impedance method, while talking, I think I was pretty clear that this particular method, and as it is for a fact that it is taken care of, or it is used in protection relays as well as the fault recorders, for the reason that it is quite cost-effective method. It is quite cost-effective. You don't have to do anything. You just have to take input from your PTs, CTs, and rest will be taken care of by your algorithms. Because all you have to do is to calculate your impedance. But is it a comprehensive solution? No. The reason being, this solution has quite a poor accuracy for the reasons that are like your CTPT have inherent errors, as we know. So these errors culminate into giving it quite a poor fault location. Here, when I'm talking about errors, or when I'm talking about inaccuracies, please bear in mind, I'm not talking about performance of a distance relay. I'm talking about performance of distance relay in terms of finding out the location of the fault. So now, keeping that in mind, so the error associated with CTs and PTs, they culminate into giving out the location, erroneous value for their fault locations in those transmission lines. That is one thing. Second thing is, coming back to the earlier slide, as we are quite aware, as we are aware, whenever there is fault, most of the times the fault is fault. That is something that happens more often than not. So in that case, you always are going to have this. You always are going to have a fault resistance. Now, finding out a value of this RF or predicting this value of RF is quite tough. Hence, the error that is associated, because we always expect something that might be this value might be good, or that value might be good. So in that case, the error that comes with it is quite bad. Just a moment. Sorry. Yeah. So those are the two reasons that give out a lot of poor accuracy in terms of finding out fault location with help of the impedance method, then you have got limited accuracy or insufficient accuracy for line parameters, like due to lack of line transposition, due to distributed capacitance, and so on. These are inherent line characteristics that are already there. Then comes your uncertainty due to your zero sequence impedance, as you cannot predict it, and it changes from soil resistance to, depending upon the area to area, the soil resistance changes, and so does this. That's why you have got quite a poor inaccuracy or a poor accuracy for online fault location or fault location in transmission lines. Now, the limitation with impedance methods are quite a lot. Like, as you can see here, the limitation is that it cannot be used in non-uniform double circuit AC transmission lines. Then this method cannot be used in HVDC line. Then in series compensated line. Then the lines with T branches, or simply the T lines. Then comes your mixed lines. These mixed lines are a combination. This is a single line running which has some areas or some fractions of overhead lines as well as your cables. Right? We'll see these things in a bit later. This is just for information that impedance method has limited performance when it comes to these particular line configurations. Then if the system is not effectively earthed, then again you have got some problem with the fault location in your transmission lines. So as we saw till now, that impedance method is fine till the time I'm trying to predict there is a fault, good. But when I'm talking about locating those faults, it's not that good. Now, what to do about it? So these alternatives are, as you can see on the screen here, these are the alternatives that people came or they actually came to they actually fall upon. So first of all is the TDR technique. For the guys who attended yesterday's session, you guys are pretty much aware of the TDR technique, and in fact it is quite a common technique when it comes to cable fault location. So it was also applied in the same way, just like it is applied in the cables, that the line has to be taken out from both ends and a surge will be injected from, and you will try to predict the location of fault with reference to the reflected wave, its shape and its magnitude. So this is exactly what they tried to do with it, but then there were some problems. Like, first of all, as we saw, that if there is a transient fault and suppose the breaker kept getting opened again and again, you will never be able to predict it in terms of offline condition or when you take that system out, because then that tree will be gone. Or even if it is touching, because that tree is not in continuous touch with that line, it's a transient one, not a sustaining fault, right? Suppose if I want to take care of that particular problem, that will never be justified with help of TDR. Second thing is, I'll always have to take that particular line out. Only then I can do the TDR technique. As you guys are aware, TDR can only be done in the offline condition with any of your transmission system, be it your cable or be it your transmission line. So that was again not quite a feasible solution, because our job or our target right from the beginning was not to have a longer downtime. Now here again that is happening. Third of all, the TDR components, they are actually quite heavy. When you're dealing with cable, that's fine. They will be of small magnitude and you can carry it. Just over your four-wheeler and all. But when it comes to transmission line, the size actually gets bigger, because you have to surge in a wave of a higher magnitude or pulses of higher magnitude. So it is not quite a feasible solution for you. Then again, with TDR technique, you have to have quite a knowledge or quite hands-on experience of analyzing or assessing those waves. So that is also one thing that makes it quite a cumbersome technique to follow. Now, so this is one option available, but let's go forward with keeping in mind the limitations that this solution offers. Second comes the time of arrival. The principle of time of arrival is actually the principle that is taken care of with the help of traveling wave fault location system itself. Now, with this particular principle, what they try to do is they try to catch or they try to detect the traveling wave or the surges that if there is a fault in between, let's say in a transmission line, in between terminal A and B, or in between substation A and B, then those waves will these traveling waves which will be generated at that particular fault point will move towards A as well as B, right, in an equal magnitude if it is happening right in between the center. So there, with reference to the time of arrival of these two pulses at these two junctions, at A and at B, not junctions, at these two terminals, the system will predict with the help of its algorithm that when the waves arrived at those particular points and where exactly that particular fault lies in the line. So of course the time of arrival has to be used, or this principle is used only when the system is online. And this is what our objective is today. We will be talking about online traveling wave fault location systems only. Okay? So what is traveling wave? Traveling wave fault location system we have been talking till now. What exactly a traveling wave is? It is actually quite a simple concept, basic concept of power system. The traveling waves are actually the transient waves that are produced when a stable power system is disturbed. As we know, every transmission line or every power system, it is comprised of an electromagnetic equilibrium. Now, whenever there is fault, that particular equilibrium is hindered. Now, whenever that equilibrium or that particular system it gets disturbed, it leads to surges. It leads to surges that flow, as I was talking earlier in terms of the time of arrival principle. Some surges will emanate from those points and they move from that fault point or that fault location towards both end of the lines. Now, what are these disturbances basically? Now, these disturbances are quite generic ones. Like you can have, short circuit fault or high impedance fault, high resistance fault, and there can be circuit breaker operations. This is also something that can be detected with, because this again hinders your running line or hinders your existing power system equilibrium. Then there are your lightning conditions, then your transient conditions, and so on. So these are this is what traveling wave exactly is. These are basically current and voltage waves, or current and voltage transients that flow towards both ends of the transmission line whenever there is a fault. Now, how exactly does this principle work? So, moving on, as you can see here, the traveling wave fault location system. Now, in this particular system, you have got 3-4 components. Like, as I was talking about, just let me get the marker. Okay, in the meantime, let me just give you a brief introduction of this. So, you have got traveling wave fault location system, right? You need to have capturing. As I said, the wave will travel to both ends. So, you have to capture those waves. So, you have to have the coupling systems that can capture those waves. Then you have to have high-speed data collection. Now, by high-speed data collection or by high-speed data analysis, that means you have to have good system which has a high resolution, which has a high data processing power. So those things are required because these are transient waves that travel. These traveling waves, mostly they travel with the speed that is almost at par with speed of light, right? That is 3 × 10⁸ meter per second. So you have to have a system that can capture a wave that is traveling at such a high speed, then analyze it too. Then the last one is synchronization. What I meant by synchronization was that you need to have a system that can calculate the time of arrival of the waves when they reach at two terminals. Like I was saying while I was taking the time of arrival. Now what exactly happens here is, first of all, whenever the system is there in the line, because we are dealing with the online system, so before installing the system, we always have to have a calibration of the line. So you always need to have a calibration of the line done before taking your system into the line. So first of all, what we do, we always calibrate it from both ends, from a breaker that is present here, then the breaker that is present here at the other end of the line. Now what exactly happens is, Why do we require this calibration? As we are telling, this is transmission line, it does not depend upon the line parameters, unlike the impedance methods. And because of that, we are claiming that it has very good accuracy of 150 meter. Then why do we require calibration? Now, as we know that in transmission line, there are a couple of things that happen over the time. Like, first of all, the sag will happen. Sag is something that is more or less not accounted for. Nobody takes into account what is the effect of sag, and because of that sag, the effective length of the line increases. Now, after that, you have got jumpers in the line. That is also something that people don't account for. But when these are of a length of 1 meter or something. When you're talking about jumpers, or let's say 100 centimeters, or whatever the length be, depending upon the dimension of the line, or depending upon how you have placed your insulators, suspending insulators. Now, what happens is, when you're dealing with line that's traveling to, let's say, 800 meters, or let's say 400 kilometers, 500 kilometers, then this 100 centimeters or 200 centimeters, it gets multiplied into the number of transmission line that you have to take into account. Then this total net value comes out to be 1 kilometers, 2 kilometers, even it goes as far as 5 kilometers. So you always need to calibrate the exact length of line after knowing. Now, how to know that exact length of line? Because the measurement that is available with the people or the design system is that the length of the line is assumed from gantry to your other terminal or the last tower, right? So then what we do to compensate for the sag and the traveling wave and your jumpers, what we do is we adjust the VOP, velocity of propagation of the waves that will be there when a fault occurs by applying these circuit breakers, by operating these circuit breakers, opening them at one end and then closing them. So by doing that, we change this velocity of propagation. By operating these breakers, you got your traveling waves or you got your disturbances, right? As we discussed before, how the traveling waves come into being. After that, you change your VOP, just like you used to do in circuit breakers, in the terms of cables, when this value matches the total length of the line, that is known to you. Because in the end of the day, I am not going to work upon the exact, let's say I told you there is a fault in the line somewhere, let's say this distance is 23 kilometers from S side. That is no good to you. What's good to you is, okay, it is between tower number X and tower number Y. Only then you would be able to take a proper action, and you can send your men directly in between this particular tower span, and you can rectify whatever the problem is. So that's why the calibration is very, very important. And I hope with this example, you must have gotten a better clarity of how exactly the things go in principle as well as in practice. Now, as it is clear to you, I think it is a dual end calculation. You have to have systems, or you have to have a detection system at both ends of the line. Then you need to have a GPS synchronization. Now, what is this GPS synchronization? Why is it required? Because as we saw earlier, in time of arrival, you calculate the difference of the arrival of those pulses, difference of the time of arrival of those pulses. So in that case, you require to have a GPS synchronization. That is, there will be a GPS system connected with your acquisition system at both ends, and they will be time sync. GPS does not require an introduction in itself, right? So that those systems will be time syncs. That means they will be detecting and calculating the time of arrival in real time. And whenever there is fault, you will always be able to know, or the system always is able to calculate the fault location system. Then we have got high accuracy. This high accuracy comes because of the solutions, because of the parameters that have been taken care of earlier. You have to have a good capturing system, you have to have good processing system, you have to have good analysis system, then you have to have time tagging. And the system is dual ending. That means the system is actually automatic. You don't have to do a manual calculation, unlike in the TDR method and single-ended method, that we will see what single-ended method is. So this is what traveling wave fault location or online traveling wave fault location is in brief. Now, as we have taken care of all the errors, so this method is actually quite accurate, very, very accurate. as it is independent of your fault resistance, I am not taking into account of any of the line parameters or fault parameters. I am not taking into account any CTPT errors because I don't need that. I'm calculating the current coming from the CT. I am just calculating the time of arrival of the surge. That is my basic concept. And independent of the line configuration. As we saw that be it your HVDC, be it anything, I don't require any of those things. So I'm good to go with the very good accuracy. Now these systems, just a moment. Nila sir, can you take care of this? Yeah, it's gone. Okay, sorry for that. Now, traveling wave fault location system, this concept was actually proposed in 1950s and 1950s to 1960s. There were so many methods or so many kits, equipments were brought out, but they could not function well because of the reasons that they did not have at those times. They did not have such a high data acquisition system, such a high data processing system. They did not have such a liberal approach towards the GPS system, because at those times, GPS was first installed or it was first used for the defense purposes by US Army, which was later opened for the commercial purposes. So that was not there. Because of these reasons, those systems could not work well, and they are not very much, they had to be rolled back. But these systems in those times were brought into the scenario by US, Japan, and China. These have been three forerunners in this technology. And there were basically three kind of technologies that were there. That is, first is fault reflection in traveling wave waveform. This is the single-ended method that we'll see later what exactly is it. Second one was time of travel and time difference. So time of travel and time difference, I believe we have covered this. So this is one of the ways of doing that. But this not take such a it could not could not be very much useful, because at that time the time of arrival or time syncing, that was not possible, as GPS was not available in those times. Then third one was your radar or pulse echo principle. So this principle is nothing but your TDR method. Okay. So going ahead. Now, so in 1980s or 1980s to 1990s, to be accurate, people came with the system that you're seeing on your right. So here you have got your GPS. You have got your data acquisition systems at two ends, as you are seeing here on the line. Let me use a pen, because these are the basics. Once I have covered it, there is not much to talk about in the system, because system is quite simple, as you guys must have seen till now. So you have got your data acquisition system at two ends, right? Using your CT inputs only. Now here you have got a fault. Two surges will generate that will flow in these directions, the traveling waves. These units are time tagged. The time of arrival of these waves will be calculated by your system, and using a master station, the brain of your system, you can easily calculate the fault location from either end of the transmission. So this is how simple the system is. So the system is simple, quite reliable, because you don't need to worry about what kind of line are you going to put on. Then the system is automatic, as I already said. The electronics, as you already know, the electronics is so developed nowadays, and with the advent of artificial intelligence, machine learning, and whatnot, you have methods, you have got algorithms that take care of things on their own. Now, the system is quite accurate, as it is independent of any of the errors that can be there because of the line configurations or because of the inherent properties of the line. So this is what a generic double-ended transmission traveling wave fault location system looks like. Hello sir, can you please shut off this? Yeah. Now, this is the first method that I was talking about, or the method that we saw earlier, type A method, the single-ended method. Here, this is a method which is very, very easy. here you put your traveling wave system at one of end. Suppose I put it at the S end. Now, whenever there is a fault, as you can see, the traveling wave, because you have only one data acquisition system, so the wave will be traveling to both ends, but you will only have one end to capture it. So at S end, one pulse at TS1 will be captured, then it will be reflected back, then again it will be reflected back from the fault end, and then it will be the second wave that you will be getting. It is just like any other methods that you have seen in the offline conditions. However, this is happening in the online condition. So calculating upon these difference between these two times, you calculate the distance of the fault from the one end. Now the problem with this particular method is, as you can see on your right, there is a waveform that is presented here. Now, how exactly to know how to analyze this waveform? As you can see, this is actually looking quite frightening. What to do with this particular waveform, because there are so many surges. Unlike what you get to see in your DDR when you apply it in cable, because you have your cables out, you don't have too many of disturbance, because your cables are when it comes to EMI or EMC, the cables are quite good. You are putting it down in the ground, so there is not too much of an interference. Whereas when you are dealing with a transmission line, even if these transmission line, whenever they pass near to each other, or whenever they are just there is so much of disturbance coming from them, even when they are in online condition. So just imagine if you have a waveform like this and you have to analyze it on your own. Now, this is one of the reasons why this could not take a flight, this particular method, because it requires a great manual expertise to pinpoint a particular fault. Now, due to the reasons that I just said, this method was not quite popular. Then came the double-ended method. This is the same method that we just saw earlier, that you have your systems put at S and R. The waves, the traveling waves that are generated from the fault location will be captured at these two ends, and from difference of your time of arrival of these waves, you calculate exact distance of the fault location from the two substations. And the added advantages that we saw earlier are like they are automatic. You don't have to do anything. The system will do everything for you, right? Then the accuracy, because it is independent of any of your line parameters, it is highly reliable because of the same reason. It is GPS synced. So since everything is fine, and you will always have your fault location done in the real time without having to face any downtime and without any additional burden to you. It is not quite feasible for everybody to start learning a new thing, especially which is so intriguing in nature. So it is quite a good solution. Now, this is just not it. Here comes the T branch configurations. As we saw, the application of this double-ended system or the traveling wave fault location system in various configuration of the line. So how exactly the system works, I'll try to explain this in a brief. Now, as you can see, you have got three terminals, S1, S2 and S3. Most of the times this line associated with S3 is just a tap that is done in the S1, S2 line, the line between the S1, S2 terminals. So you have got three data acquisition units, DAUs for short. Please, when I am saying DAU, please consider it as your acquisition system or the sensing system that will be placed at your substations. So you will place your DAUs at these 3 points. So whenever there is fault, as you can see in the first case, the fault is just at the very center. In the top diagram, you can say fault is exactly at the T point. So in that condition, you will already be having a distance between S2, distance between S1 and S3, and distance between S3 and S2. Now, with the help of time of arrival, the equivalent distance is calculated by calculating the time of arrival between S1, S3, between S2, S3, and between S1 and S2. And with the help of that, you can get exactly where this fault lies, even if it is on the T line or it is anywhere in the line away from the T point. So this is how the system works, with using the time synchronization and using the inputs of all the three data acquisition units or DAUs. Now, next comes the Type W or wide area monitoring system. This type area monitoring system, let me switch on the whiteboard as it is required to clearly understand the system. So you have got you're traveling with, this is suppose a fault. These are your systems, right? Now, whenever this fault or due to this fault, whenever there is a traveling wave coming out of this fault, this will go along the line, right? So to the nearby DAUs, data acquisition units, these waves will be received. Like suppose a fault was there, the point F, as you can see here, F. So the wave will be received at N, at K, at V, at Q, as well as at P. Now, during calibration or during configuration, we had already defined the distance between P and N, right? N and K, N and V, and N and Q. So these waves will arrive at these points and will be sensed by our data acquisition units, as well as the depending upon the time of arrival of these fault points to these data acquisition systems, you can easily calculate the exact point or exact fault location of your fault, basically in your transmission line. Now what you have got is, you have got a wide area system. How it is different from your double-ended method is, it is just an extension of it. So instead of using it just in between two substation terminals that are sharing one common line, this has now been extended over a wide area, and it can incorporate more than 250 number of substations. Okay, so more than 250 substations can be networked at one place to locate the traveling wave, to locate your transmission line faults in online condition using the traveling wave technique. So this is how this system is good. It is actually, it does not put any additional cost on you, because this particular feature is already there in the software. So you don't need to pay anything extra for that. If you already have this system installed in your in your substations, concerned substations, you can always have that data in your master station, and you can have a SLD drawn just like the one that we have here. It is almost like an SLD, and you can calculate the fault location that happens anywhere in the line of the substation, whichever line, if that line is shared by the substations that have the data acquisition units. And it quite works as a data backup, or just for the sake of the same, or for the sake of discussion. Also, it acts as a good backup, because let's say a fault occurred here, and for some reason, let's say for some hypothetical reason, and it could not capture that particular fault. So that particular waves will go to K. K will capture it. Okay, let's say P could not capture it, so Q will capture it, and it will do the associated calculations from N to P. Same will be done with N to P. Same will be done with N to K. So in this way, this is what we meant to say by having a backup. Now comes mixed line. Nila sir, can you clear the whiteboard? Yes, thank you sir. Now comes the mixed line. Now what exactly mixed line are? As we saw that mixed line can be mixture. Basically, it is a mixture of lines. So you can have an overhead line, then you will have a cable in intermediate cable, then you have a connecting overhead line. Just what is drawn in the diagram. The dark one right in the center. This dark line is depicted as a cable, and the shallower lines or the narrower lines are the overhead lines. So this is what comprises of a mixed line. It can have underground, overhead, underground, or you can have any kind of configuration that you have. Even in those circumstances, our system works very fine, and it localizes faults without any inaccuracy to your system. So this is kind of range that we have. Now that is quite critical also is the HVDC system. In HVDC system, as you can see over here in the diagram also, we again capture the transient waves or the traveling waves coming out of these capacitors. This just before this shunt reactors, the waves that are coming out of these capacitors and getting grounded. Now it has to be done over here because of the your suppressing capacitor that is associated with your inductive CT. It has to be done before that inductive CT, because otherwise this particular suppressing reactor, as you are seeing in between C1 and C2, it actually quenches these traveling waves. So this is captured here, and with help of these external CTs that are placed in the field using a junction box, right where these wires are grounded, these wires are run back into the substation, into your control rooms, where you can easily monitor the traveling waves if there is a fault in the HVDC lines. So it again uses your type D
Seems Jayant somehow got disconnected, and we are trying to bring him back online. Jayant, are you back? Jayant? Yeah, Jayant, carry on.
Sorry, sir. Due to some technical glitch, actually yesterday, not even yesterday, last night we had quite a downpouring, and with Andhi and Tufan. So due to that, there is a problem with network now today. So as I was saying, the single-ended method is inherent in the double-ended method. If whenever you're taking a double-ended method, single-ended method is inherent inside the system. So you don't need to worry about anything else. Okay, it's not a feature that you have to buy in addition. It is just an algorithm. It's just a logic that is already there. It's just that single-ended method is quite overwhelming. It can be quite intriguing, and it requires a lot of technical ability to get to a meaningful solution without calling the system not working bad, or without calling the system nonsense. That's why double-ended method is proposed, or double-ended method is suggested to go for, because there the system is good enough with the kind of algorithms that it has. It is good enough to work on its own without giving you additional work burden. All right. Now, this is how the inputs are taken into the system. As you can see here in the first one, or in the left one, you have got direct current input. So here we directly take input from the CTs, that is our field CTs, primary equipments, and we directly take that input in our module, and then that terminal can be here to other protective devices, right? But this is something that not too many people are keen to offer, or not too many people are interested to go with. So we suggest non-intrusive current solution. So here you have got your CTs. Now you have got this black equipment that you are seeing hanging right in the bottom, right? This is a clip-on CT. That means there is a clip. All you have
It seems we have lost Jayant again. Please bear. Yeah, just join back. Jayant, are you there? Hello, Jayant. Friends, please bear with us for a few moments. Yeah, Jayant, I think you're back. Carry on.
Yeah, at Giants end there is some power issue, so he is reconnecting.
Sorry for the technical glitch once again. Am I audible now?
Yeah, we can hear you, Jayant.
Okay. So this is how the solution, this is how efficient and good the solution is, that you do not require a shutdown even while the installation. Now moving ahead, this is how the communication is set up. As we saw, communication was the reason why this particular technology or mechanism had to be rolled back even after getting initiated in 1950s and 60s. So communication systems, as we know, they can be modem type or a dial-up kind of communication you can have, or you can have a point-to-point communication. You can have a fiber optics or a Ethernet kind of a communication between your the square box that you are seeing in the bottom. These are your data acquisition units, the DAUs I have been telling you about, and the system or the monitors as you are seeing over here. These are your master stations. Yeah. So this is the communication types that are available. Then we have our Ethernet kind of communication. So they can communicate with the master station using a LAN. That is being depicted in the system. Now, after taking care of the communication, and we have got some sample pictures and sample signatures that we have captured. By we, I mean to say our channel partner. We are the channel partners of Kehui, and Kehui has an experience, as you saw, that Chinese manufacturers, they were the pioneers in bringing this technology, and Kehui is one of them. And it has done more than 3,000. I'm trying to stress on this. It has done more than 3,000 installations worldwide. So it has got extensive experience with the system, and its system is quite reliable. So these are some waveforms that I want you guys to see that we have tried to incorporate here for your better understanding of the system. So this is type T 500 kV series compensated line. Now I have to use the whiteboard here to show you things. Now in here you can see in the waveforms you have so much disturbance, right in the very middle or throughout. This is this particular line, if you can see the dashed line here. This is your time of arrival, the first line here, and then this is your second line, the dotted line in vertical as you are seeing. So this is first line at one end, then this is the second line from the other end that is received by our data acquisition system. And then you are seeing all this vibration in between. It is due to your series compensation. Series compensation is like your C and L in series, right? So they give rise to these oscillations that you are seeing here at both ends of the line. And here at the top, as you can see, this was in between two substations in China, and overall length is here. And when the fault occurred, the length from or the distance from this end is shown here, and the fault from this end, that is the other end, is shown here. So exact line length can be measured. Then the system, our software, also has a feature. Nila sir, can you take out the board? So our system or the software also has a feature of incorporating all the towers or your total tower configurations, right from the gantry to your last tower. So when you incorporate that in an Excel sheet, it is actually quite easy to do. And whenever you do that and you install that in your system, or if you load that in your system, whenever a fault occurs, that fault will be shown in terms of kilometers, as you are seeing here in this particular system, as well as in terms of the as well as in terms of its position or location in between two towers. So that is one way of seeing things, and that is how the system is analyzed. Then we have got type D. This is high resistance fault. This is a totally different kind of fault. Line to ground kind of a high resistance fault was there. So here, right in the middle, you can say a fault is depicted, and total length of the line is there. And just like what we saw in the last picture, that subsequent or the separate line distance or the distance from that particular fault has been shown for the associated substations. Now this comes with the third one this is the fault in your 500 kV HVDC line. Here also the same depiction is there, length is there, then you have got your distance from the subsequent substations. Then comes your lightning transient. Now whenever there is lightning transient, it is actually quite efficient or good enough to capture these waves. And with lightning transient, there is a peculiar nature. If you can see over here, you will always see disturbance, or you can see a coherence in all the three phases, in A, B, as well as C. So that is also a depiction of line transient. But line transient are always, they always have a very high current surges. So, and they are captured with our system, and it can localize it. Where exactly has this lightning occurred in your transmission line. Then comes your circuit breaker operation or circuit breaker status feature. It is also there. This is the feature that is used during the calibration purpose. You have to open circuit breaker at the both ends of the line. Then you will switch on one of the breakers. That particular operation will give rise. Just let me use this whiteboard once again. I just want to give you a better clarity of the system instead of just walking you through. So here what will happen, this will be your first wave or first surge received, and this will be your reflection because of the open circuit. As it is, as these are the current waves, that's why you are seeing the opposite polarity in the surges that are received by you. If had they been the voltage surges and the fault had been a open circuit fault, you would have received the same polarity of the surges at the end. So this is what I wanted to show, that it captures circuit breaker status or circuit breaker operations also. Nilesh sir, can you take out the whiteboard? Next comes type A kind of a fault. So this is your fault of single-ended. As you can again see, so much of a transient is there. This is also happening in online condition. Please don't confuse it with the offline traveling with fault location method. This is happening in online condition only. So you can see the kind of transients that you are getting. Right? Now there, with this particular method, being able to decide where exactly to place these two cursors to be able to pinpoint the fault location is quite a tiresome job. That's why we try to discourage people to go with this method. Whenever you are going out to purchase a particular solution, of course, your system is very critical and it is quite precious to you. So you please go with the double-ended method as it is most efficient. most reliable and accurate one for you. All right. Now, these are some examples that I wanted to show you. This is again one of the examples of type A method or single-ended method that is there. Then comes the feature of a system. I just wanted to give you a brief overview of how our system looks like. As you can see here in the bottom, you have got the front end of our system, and here it is the back end of our system. The system has got supports 8 lines. When I say one line input, we have got 3 phases, right? So one line having 3 phases, and it has the total capability of taking 8 line inputs. That means total 24 analog inputs can be inserted. They are totally configurable. That is, input can be taken from CT, as we saw earlier. We have got 2 input types, basically primary CT input and secondary CT, where we use our clip-on kind of CT or directly taking it from your CTs. That configuration is there. We have got a very high sampling rate of 36 megahertz. Then we have got inbuilt storage of 500s. Then this storage can always be uploaded, or a backup can be formed in your PC or in your master station. Master station is basically your PC that will receive input from all your associated data acquisition units. That is all that is all about master station. And let me tell you how the master station behaves with all these data acquisition unit is like a client server kind of a relationship is there. So your master station is a client, and all your data acquisitions are the servers. So they keep on communicating with each other. They keep on sending their values to the master station only. Okay. And if you want to monitor the particular system at more than one locations, that means you want to have more than one master stations, you can always have it. That is not a problem. All right. Now, apart from these things, you can have 2 NO contacts for alarm, to get alarms and all. Now, you have got communication support with your PLCC, fiber optics. You can have a GPRS module. So whatever communication system is available in your substations, I can assure you we will comply with that. Then you have got protocols like IEC 61850 that makes it SCADA compatible. And you have got 101, 104, so you have got PLCC and everything that is available in terms of communication. Then for time synchronization, we have got internal GPS module. External GPS antenna has to be placed physically, and it has already got internal GPS module with the help of which time tagging is done, right? That we have seen while discussing the principle of traveling the fault location system. Now, it supports DC as well as AC power supply, as has been shown over here. It has got local LED displays, okay, for power, fault, for communication, for detection of a particular, surge. Every time something is there, local displays are there. You have this local LCD display and local push button, with the help of which you can configure your system even locally as well as remotely. With remotely, you can do that by sitting in your control room. So this is how the system configuration is there. Apart from that, you have got Ethernet port, 2 Ethernet ports, one RS-235 port for the communication or for local communication. Suppose you have got your laptop or PC that has the supporting software, and you just want to do some configuration change, or you just want to have some data backup, you can do it any given day. As you can see here in the installation, I just wanted to show you how the system exactly looks like in the picture. So you have got a 19-inch rack, as you can see, which is a standard for any of the existing panels. So it's not like you require some big mumbo jumbo to put this in place. This is a simple panel, a simple box. So it will be placed in any of your existing racks. All it requires is a 19-inch rack system, which is quite standard here. So, and you have got these secondary CTs, as you are seeing over here, the black CTs that are hanging with the wires. So these grayish wires are actually your CT wires, and that are coming from the field. These are primary CT inputs, and these are your system inputs. That is, these clip-on CTs will take input to the data acquisition unit, to the both end of the substation. So this is setup. This setup will be there at one substation, and similar other setup will be there at the other end of the line. at that substation. So this is what a system is all about. Then when it comes to the software features, as we saw in the earlier diagram, you can have such a you can have this background and all these things just to see the data. Everything will be there. Even a smallest disturbance can be seen over here and can be accounted for. So that is one thing. Then apart from that, when it comes to software, you can have your type W that we discussed, the wide area network that can comprise of more than 250 data acquisition units. So you can, if you are a transmission utility, you can have a pan region or pan India for that instance, that kind of a network. So these are good solutions for you, that after taking input from all the substations, you are monitoring your system sitting at one place, right? And you can also have more than one monitoring system. So these are some features that make our system quite unique. Apart from that, you can also use GPS location. If you can insert your GPS location of your towers, you can actually see where exactly the fault is in physicality or in principle. You can always see that with the help of software. So that is the same. And whenever there is a fault, or you can actually draw your system in just like a SLD diagram, right? So these are some features that I haven't actually shown over here, but I think are actually good enough, or are something that you should always know, so you can judge the system better. Now, this is all from my side in terms of online traveling wave fault location system. Now, Nilesh sir, I can.
So Jen, from your side, this is finished.
Yes,
I
sir.
think when it came to the questions, we had been very efficient today. I think most of the questions are answered already in chat.
Yes,
But if there are anything more that we can take online, I'll just check.
Yes.
Yeah, some of the questions are there which can be taken up, Jan.
Yes, sir. Please, sir, tell me.
Just one second.
If it is possible, sir, just dictate me the questions. I'll just answer it.
Yeah. So it is at the very beginning, Mr. KK Murthy has asked that is it a online or offline instrument? So yes, sir, it is an online instrument only, and hopefully you have understood the applications. But Jayant, you can explain, because there are Mr. Murthy sir and one more person, as I have seen, he has asked how does it measure the auto recloser function, if it is auto recloser or SOTF function. If there is some fault, how we will get the signature, that sort of thing.
Okay, so Murthy sir, I believe that first part of your question has been covered. That the system is online system. So whatever is happening in online state, that is in real time condition. So you are getting a fault location in real time condition only. Now, whenever there is a fault, let's say a fault occurred, so the traveling wave will emanate from the fault point to both ends of the transmission line. Now, after reaching the substation, let's say I talk about substation A only, all right, only one end of the line. So there, it will be sensed by my system, all right. And after, when my system senses it, at the same time the circuit breaker is also sensing it, because the input is being taken from your CTs only. Now, that after taking the input from the CT, the relay will get notified, and then relay will take action on the circuit breaker, and the circuit breaker will get opened. The same mechanism will be followed at the other end of the line, at the other substation. So circuit breaker is open, that is fine. Now, as we have the auto reclosure function, so auto reclosure function, after waiting for the particular program time, right, for the time that there is for the auto reclosure function, it will try to close. If it is transient fault, it would have been gone. It will be gone. You won't be able to find it now. Okay, so that is the thing. If it was there, if it is transient, it is gone, and when auto recloser try to close it, it will get closed. That is fine. But the transient that or the traveling wave that our system captured, that data with that data available with you, you will always be able to localize the point or the point of the fault location or the point of the for transient fault. If it is persistent fault, then your breaker will open, auto recloser will try to close it, and again it will get open because the fault current is already there. So this is how the system behaves in terms of transient as well as persistent faults.
Okay, Jan.
Was I able to answer it?
Yeah, I think you are quite clear. Now, also Mr. Azaz Zikani has asked in impedance method how the pinpointing can be done. So instead of answering that, you can tell us that in impedance method how much accuracy we can get, and in a rough way, and in our system of TWFL how much best accuracy we can get.
Okay, sir. In online traveling wave system, you can expect accuracy or guaranteed accuracy is at best is at 150 meters plus minus. That means almost 1 tower span. If I'm telling you that, let's say, for example, hypothetical situation, if we consider we have a fault between 19 to 20, so I will give you a fault. This is the best accuracy that I'm talking about, will be from 18 to 21. So 1 tower span plus and minus. That is what that is how good the accuracy is. Whereas when it comes to impedance method, unfortunately, sir, it is existing or it is a method that we use with our distance relays and data fault locators. That is fine, but the errors that are introduced due to this inherent CTPT error, CTPTs always are going to have errors, right? Because of the magnetization characteristics of theirs. So those errors are always there in the calculations. Then you have got error introduced due to the fault resistance or the fault resistance that happens. Like when there is line-to-line fault, there will be resistance of the arc. When there will be line-to-ground fault, the resistance value will be different. Then again, the value of the resistance of this fault or fault resistance will vary from soil to soil type. Suppose touching a tree, or when it is touching your, let's say, tower body, the fault resistance will be different, sir. And whenever you are calculating V by I, you get the fault in terms of your line length. Okay, so lower the length of the fault. And longer. Okay, this fault location or the error introduced for fault location, so they will keep on growing or they will keep on going up. But in our system, 150 meter plus minus 150 meters, that is the best accuracy offered by our system, is the accuracy irrespective of the fault resistance of the kind of line that you are dealing with. As we have already seen, impedance method does not work very well with the HVDC lines or the other line configurations like T kind of a method, or T, if you have got a T line, it won't work very well. Okay, so these are the various parameters that are considered when we are saying that our system is much better in terms of locating the fault as compared to the impedance method.
So there was one more related type of question that on this system. There was one more question on the from Mr. S. Sharma, that for time synchronization in the device, we are using the GPS. So SNTP things will be sufficient, or PTP will be used? I think SNTP is more than sufficient for our purpose.
Yes, sir. SNTP is good enough, sir. It will do.
One more question was there related to like that. Okay, if we miss the GPS signal because in some condition like rainy condition, or there are too many clouds, so or if the system is missing the GPS signal for certain time, certain period of time, so what will happen?
So this is actually kind of a worst case scenario. Just for your information, most of the time, even when the clock goes out of clock never goes out of synchronization. So let's say, and because the substations are far away, assuming that substations are far away, that when this particular thing happened, so suppose cloud occurred at one end of the substation, okay, and your GPS did not work for, let's say, any hypothetical reason, the waves will be captured there.
So you mean to say that GPS is something like that, it will be either end, it will be available, and moreover to
Yes,
that, whatever the last signal we have received, based on that it will be synced. And
Yes,
the instrument is having that real-time clock. Based on
Yes,
that, some minor microsecond difference may happen, but
Yes,
it
sir.
is not supposed to be, because GPS signal out of sync for a very long duration, maybe months or together, then only some milliseconds
sir.
mismatch may happen. That you
Right.
mean to say.
Yes, sir. Exactly my point.
And there
Momentary,
is one more question. Yeah.
momentary GPS loss is never a concern, because once you have synchronized your clocks, they'll keep on working in the same fashion for a long time. Just exactly what you said. That's all I wanted to say.
Okay. One more question was asked by Mr. Umesh Kumar, who has asked, okay, what should be the minimum length of the line for using this device? And similarly, one more question it was there, okay, that whether we can use this in 11 kV lines also. So, as per my understanding, there is no lower voltage level where we cannot use the system. It is not like that. And if we talk about the minimum distance, it is the cost versus benefit, something like that. Am I correct, or you want to add something on this one, sir?
Exactly, sir. That is the primary factor. You always need to have a good return of investment. That is the prime concern of everybody that is present over here. So, putting that in mind, there is actually one more thing that is concerned. That if it is always better that the length of line is be greater than 10 kilometers, then it is actually quite efficient. Accuracy will all, I'm not talking about accuracy wise. Of course, that is the point of ROI, the rate, return of investment is always
Return on investment and line length, maintenance of the line,
Yes,
from
sir.
that angle you are talking.
Yes, sir. From that angle, I'm talking. It is always good if you have a line which is greater than 10 kilometers. It is actually good. So, and when
Even I think
the first
even a 5 kilometer or more line also can be used, but it
Yeah.
depends totally upon where the utility wants to use it.
Yes, sir. And answering your first question, sir, about the voltage level. So, as I discussed, this voltage level has nothing to do with our system, because we are capturing traveling waves. So, if you are, if you are sure about the system, or if you want to use the system, you can always use it. Voltage level is never going to be a concern for the system, because rather in lower voltages you are going to have a higher fault currents. So,
Yeah. So one one more question asked by Mr. Rana Singh. He has asked, is it useful for detecting the series faults such as broken conductor or something like that? I believe question will be yes.
Yeah, actually, with broken conductors, sir, actually pinpointing is quite tough because the system that works, this is actually quite something that I cannot, answer upfront because it is there is a mechanism and it is
Depending upon the actual fault type, so totally broken or broken up to line or line to phase or line to ground, how
Yes, sir.
it has happened, you want to mean to
Yes,
say
sir.
on that fashion?
Yes, sir. Yes, sir. Yes, sir.
Yeah. Okay.
So
There was one more
concerned
question.
person, pardon me, sir. So the person, the respected sir who asked this question, you can, sir, put down a mail regarding this. If you require a further clarification, we can have a discussion over this.
Yeah. That obviously we can do. Jayant, if we want to use this system in HVDC, and is there any special calibration procedure for the HVDC separately, or it is similar to that normal way as we are doing the calibration for AC lines?
AC lines only, sir. There is no special provision for anything. Guys, this is actually a very good question. So, honorable sirs and madams, so I just want to tell you, traveling waves and standing waves, these are the same things that we have read in our, undergraduate courses. So, these are the same traveling waves that are flowing, be it in AC line or in HVDC line. It doesn't matter because these are electromagnetic waves who travel at the speed of light. So behavior of these waves with respect to the lines or the type of system where you are putting it, like in different line configuration, it won't matter. This is just a crust of the story. So I hope with this statement I am clear, sir.
Yeah. So it is the velocity of propagation is the major thing what we need to calibrate for getting the exact fault location. That is the thing, and the total length of the line. It should be known to the best possible way. So by using these these two helpful information, we can get the most accurate or calibrated result, you can say.
Exactly. Exactly.
Yeah. And the another thing is that this traveling wave. There was one more question: why the traveling waves are entering into the? Actually, that thing is that it is the traveling wave when it is getting generated at the time of any fault. It starts traveling from the fault point through the conductor. So whenever it is getting a medium, it will propagate to any direction. It does not look whether it is a healthy zone or unhealthy zone. So traveling wave is getting generated at the fault point and then it is traveling. So it doesn't look forward for whether it is a faulty zone. So only I'll restrict myself in that zone. It is not like that. So it will travel, and all the way it will travel. It is having the strength to travel until and unless it totally gets attenuated and totally dies down. So that is the thing. It will travel and even enter. It can be visible even into the healthy zone. So it can cross even the substations as shown in the T junction things, or especially in the YDR networking zone, where it can even pass through a total substation. So it depends upon the substation configuration or all the things, whether the sun shifters are there, whether CVT is there, all those things are there, but it can travel. That is the major thing. So from the fault point, it will generate and it will travel. Our target is to capture those traveling waves at the most efficient way and plot them so that we can do the measurement of actual distance of the fault, distance to fault. So Am I correct, Jayant, on this fashion?
Exactly, sir. Rather, we can have, with your permission, sir, I would like to just explain an analogy here. That whenever we are standing at a seashore, so you always see that the sea water, the water is always coming towards. This is, you can just assume that this is what the electromagnetic equilibrium, what I was talking about. There is, whenever there is a flow of current, AC current, as we already know, there is a electric wave as well as magnetic wave going along the, going in the direction of that current, and they are all in 90-degree perpendicular to each other, right? So you just consider this wave flowing just like the water from the sea is coming towards the shore. Now, whenever this, whenever it reaches the shore, okay, suppose it is not like when I'm talking about shore, I'm not talking about the beach. I'm talking about the, all kind of boulders and big kind of scenery things that we see. So the water will come here, it will strike against that particular boulder, okay, and the water will rise up. The splash will be everywhere. So this is exactly what TWFL is. Your system was working fine and everything, suddenly a fault happened. Okay, that electromagnetic balance or equilibrium is gone. This is that transient, this is that splash, which will travel towards both end of your transmission line from that fault point. Okay, and we have to capture this splash. I believe with this analogy, I was clear with the idea. So we are not injecting anything. It is happening inside the system only. We are only sensing it. We are actually trying to acquire it at the both ends, time tagging it. By time tagging, we are trying to time synchronize it, right? You guys are in transmission system, so you guys are already time tagging or using GPS clock for your distance release or your differential release, right? So this is exactly the same thing that is done over here, and this is what the system is. Sir.
So